Okay. I think it will take a few more seconds. Checking if everything's, yeah, I think we're live. So yeah, thank you, Anna Maria, so much for joining and for volunteering. Yeah, you can take it away.
Okay, well, thank you for inviting me and for hosting this presentation. My name is Anna Maria, and I'm a PhD student at Imperial College London. I'm in my final year. And I'm working at the intersection of privacy and machine learning. So a part of my research has focused on profiling attacks using deep learning. I've also looked into the security of client-side scanning systems, and some of my work at the moment is focused on devising new attacks against machine learning models and against query-based systems. Now, the work I'm presenting today is the product of a collaboration with researchers at Imperial, Oxford, and the University of Naples in Italy. So with Federico Monti, Stefano Marone, Xiao Wendong, Michael Bronstein, and my advisor, Yves-Alexandre Mourgeois. To give you the context of this work, and please feel free to interrupt me at any time if you have questions. Today, our interactions are increasingly mediated by technology as we use our mobile phones and smartphones to communicate with family and friends. During the pandemic, more recently, we have been using video conferences to work remotely, and even our offline interactions could be tracked by contact tracing apps, exchanging signals when we are in proximity to other people. So as a result of the increased use of technology, data about our interactions are being collected on a large scale, both for business and research purposes. And from now on, by interaction data or metadata, I will mean a record or log of an interaction, which consists of pseudonyms of two parties that are communicating, the timestamp of the interaction, and maybe other information, for instance, the duration of a phone call. And I'm saying that these data are being collected for business purposes because, for instance, mobile carriers collect location data and timestamp data in order to route calls. Interaction datasets also have research applications. So for instance, they have been used to estimate population density at specific times and locations. And this can be very useful when, for instance, census data is not available. They have also been used to forecast the spread of epidemics. Yet, such data is very sensitive because it's very granular. It reveals who we talk to, who we meet, when, for how long, and this can be very sensitive information depending on the situation. And furthermore, other information can be predicted from interaction datasets. There is a lot of research on the topic showing that, for instance, someone's significant other can be revealed from patterns of interaction. And the Snowden revelations a few years ago have drawn the public's attention to the bulk collection of mobile phone metadata. And an important thing to note is that even though metadata does not contain the content of an interaction, so like the recording of a phone call or the text of a message, privacy advocates have long argued that metadata are data, and I quote here. So for all these reasons, the release of interaction data can be very problematic if the data can be linked back to people. So an important question at this point is, like, given the sensitive nature of interaction data, can practitioners like data analysts or researchers use it? So let's say a company wants to share data with a third party in order to analyze some patterns. And in several jurisdictions, interaction data can be shared or sold to third parties without the consent of users, so long as this data is anonymized. So there is this term anonymization, which means that data can no longer be considered personal data and can be shared freely. So the natural question at this point is what counts as anonymous data? And according to technical guidance in the EU, anonymization is defined as resistance to certain attacks. For instance, linkability attacks, where the idea is that if I can link a record in a data set that's freely available with other information available about an individual, then the data set will is unlikely to be considered anonymous. And there is a lot of nuance here, and in practice the technical guidances can be subject to the interpretation of the courts, but this is the main intuition. And this intuition has been quantified in privacy research through re-identification attacks. And there are a lot of attacks out there against different types of data. Re-identification attacks basically use auxiliary information about someone in order to identify them in a data set. And most of the existing work falls into what we will call matching attacks. The idea of a matching attack is that the auxiliary information available about the user is either exact or slightly noisy and is usually stable over time. So for instance, zip code, so the famous re-identification of the governor Weld by Latanya Sweeney used, among others, the zip code of a person, and this information tends to be stable, at least across short periods of time. Social network structure has been used, so like, for instance, attacks have tried to identify a node in a graph based on the number of friends of the node and the number of friends of the friends. Also, time allocation has been used, so like 4 points of precise information about a user were shown to be enough to identify them in a large-scale data set. Like 95% of more than 1 million people could be uniquely identified based on 4 exact random points. Now, due to the nature of interaction data, like this timestamp information attached to it, we argue that profiling attacks are more meaningful to study. And profiling attack basically assumes that the auxiliary information and the data set which is being scrutinized come from disjoint time periods. And we argue that by relaxing the assumption that the information needs to be exact or from the same period, our work broadens the surface of the attack. And okay, so what we're doing here is to propose a profiling attack model for interaction data, where we switch from the tabular representation of interactions as a series of logs with parties and timestamp to a graph-like representation where nodes are entities that communicate, or users, and there is one edge between the user for each communication. So here we show that some people tend to talk more with one another than others by using a thicker arrow between them, or maybe I'm always calling someone but they never call me back, so the arrow between me and the other person will be very thick, while the other way around it will be very thin. And the idea is to represent the behavior of a user across a time interval using how to say the interactions between the user and their contacts, the contacts of their contacts. So like the original user is the yellow one here, the contacts are the gray ones, the contacts of the contacts are the purple ones, up to k-hops. And this is what we will call the k-hop individual interaction graph, which is here indexed by this time period. And the hypothesis of this work is that the behavior of users is at once regular over time and unique enough among other users to allow them to be identified. So in this work, we assume that an attacker, so a malicious agent, would have access to a data set of k-hop interaction graphs. So here I'm showing 2-hop interaction graphs from a given time period about n people. So there is one graph for each person and another graph of one of the people in the data set, let's say Alice, that comes from a completely disjoint time period. And the goal of the attacker is to identify Alice, so the target user in this data set. And we will study questions such as what's the impact of the time delay between the data set and the target user, the impact of the population size, and others, as I will present later. And the intuition of how this attack works is that we will compute vector representations or embeddings about the user in the data set and in the auxiliary information, and we will match them using nearest neighbors. Now, how we actually do this is quite a technical challenge because interaction data can be very large scale. Like we can, if we think of data sets collected over a few weeks, they can amount to millions or tens of millions of interactions. Another thing is that the nodes have no features. So here we just have edges between graphs. And what we'll do here is actually use deep learning to represent this graph information. So both to structure it, to aggregate it, and to do the matching. And these methods, in order to scale, they need to use node features, and the features need to be informative. And another important aspect is that data sets such as interaction data usually have some in-network people, so people about whom data is collected, for whom a lot of data is available, so you can summarize it into node features, as well as out-of-network people, so people about whom not a lot of data is available. They're just adjacent to people who participated in the collections. So we will actually perform a pre-processing step where we simplify let's say a 2-hop interaction graph to a smaller graph where all the nodes have features. And then the features in question are a set of hand-engineered features that summarize the information about the communications of the individual. So stuff like the entropy of the call contact graph, the number of contacts for calls, the number of contacts for text, and so on. We used very few features, although we could have computed a lot of them because we wanted to develop a fairly robust method. Like we wanted to understand what could be done using a fairly simple approach. And then the idea here is that there is this k-hop information available about a node, and we want to aggregate it. And so we used a deep neural network specialized for this type of data called a graph attention network, where the idea is to, so for instance, if I want to represent a node in the graph, I will aggregate the features of the neighbors, and then these features can be weighted depending on their importance, so to say, for the metric that we're optimizing for. And then we can propagate these features using multiple layers. So this is what is called a propagation step. So we can aggregate the information several times. And an important thing that we had to figure out here is how to optimize the embeddings to perform identification across time. So what we're trying to do is to see if we can optimize for the accuracy of matching this graph against n other graphs where the embeddings come from completely disjoint time periods. So for this, we used what is called a triplet loss. the intuition is that we can extract embeddings, for instance, from different weeks of the same user, and we're trying to push them close to each other and quite far away, or as far away as possible, from the embeddings of different people in any time period. So the triplet loss has been used for classification tasks where there are multiple pictures available or instances of the same entity. What we're doing here is looking at different views of the behavior of your user, where different is across different time periods. And actually, we're using disjoint time periods here. And this is the how we optimize the weights of the neural network. And finally, we report results on 2 data sets. So the core of the paper is done on a mobile phone interaction data set composed of 3 hop interaction graphs. So we looked at 1 hop, 2 hop, 3 hops from more than 40,000 subscribers of a mobile phone carrier. And this was collected across 35 weeks. So it's useful to think of this data set along 2 axes. So one is the axis of users, and the other one is the axis of time, so the temporal axis. We selected one part of the data set, so 15 weeks, which we assumed would be available to an attacker. This part of the data set is used to train the model, so to sample embeddings for the triplet loss and optimize the embedding model. And then we take the last week in the data set as our reference week. So this is used to compute weekly embeddings of people in the data set. And then the auxiliary information that would be available to the attacker comes from one of the target weeks, so one of the remaining 20 weeks. And we will vary both the number of hops available to the attacker, as well as the distance between, so the time delay between the reference and target week, to see its impact on the re-identification rate. The main result of the paper is that the fraction of users that can be correctly identified within rank R, so the correct candidate is retrieved within the top R matches using the L2 distance between the embeddings. So this probability is very high when using 2 hops, and it is this point here. So P2, P for K equals 2, is more than 50%, which means that more than 50% of more than 40,000 people can be uniquely identified within rank 1. And we can see that even using 1 hop interactions, more than 14% of the individuals can be identified, and that the probability of identification increases with K, but there is a decreasing return, so to say. So we believe that this is probably due to our model. So either our model doesn't scale very well with K, or information about faraway contacts, so 3 hop contacts, is less informative about an individual than the closer information about them. And we also see that the probability of identification increases with the rank. So if we allow for a few mistakes, like we want to retrieve the correct candidate within the top 10 matches, then the probability increases by a significant margin. In the next, so before I move to the next experiment, I wanted to show the results of a comparison with previous attacks on mobile call graphs that did not use deep neural networks. So we believe that this high performance that we see is due to using these powerful methods. And there is a previous attack that tried to link nodes across graphs in mobile phone data. This attack was framed as a binary classification task. So given two nodes, do they represent the same entity or not? Well, what we did is our evaluation scenario is re-identification. So we try to identify a person among n. And this method used random forest and hand-engineered node pair features to perform the binary classification task. The features used are based on the histogram of degrees of a user's neighbors. And we can see that our method outperforms this baseline both on the binary classification task as well as on the rank R, so like our re-identification task. Unfortunately, the figure on the right shows a bunch of baselines. But yeah, what you should look at is this BPIAG is our method, so behavioral profiling, and SHDay is the baseline. We also augmented the baseline with the hand-engineered features that we use, so the Bandicoot features. And we can see that even when using those features, the baseline performs worse. Now, moving on to our results, we also looked at what happens when we vary the time delay between the data set and the auxiliary information. So in the previous experiment where we obtained more than 50%, we assume that there is 1 week of gap between the data set and the auxiliary information. Now we will vary this gap from 1 to 20 weeks. And we see that the probability of identification decreases slowly with the time delay for all values of k. And however, even after 20 weeks, the probability of identification using 2-hop interaction data is almost 25%. So a risk still exists. And interestingly, we observed a slump for some of the target auxiliary weeks. And in a post-hoc analysis, we found that these weeks correspond to national holidays, which suggests that our model is perhaps sensitive to changes in behaviors that are due to outside factors. Another hypothesis that we changed now is the one where we assume that only 1 week of data is available to the attacker for the matching. So here we assume that more weeks would be available, starting from the week after the data set up to 2, 3, 4, 5 more weeks. And we can see that when the attacker has access to more weeks of auxiliary information, the probability of identification increases, but it plateaus quite quickly. And after a time, it even starts decreasing very slowly. Probably suggesting that far away data is less informative for the identification task. And another thing that we can ask is, how does the attack scale with population size? The population size. So like in the default experiment, we have a population of more than 40,000 users. Now, how would that scale if we were to increase the population even further? Now, this is not an experiment that I carried out. However, we looked at the curve for the data that we have, and it could be extrapolated. What is interesting to see here is that yes, the rate of identification decreases as the population size increases, but the rate of decrease goes down as well. So we can see that the decrease slows down. And now I reached to one scenario which I find very interesting because it shows the applicability of this attack to different scenarios. The scenario considered so far is A, here, where there's a few weeks of training data, some weeks for validation, so to early stop the model and prevent it from overfitting, and then the test data, which we report results on. We use the same users for train and test. So the assumption here is that the attacker has seen a lot of training data about the individual they're trying to identify. However, using embeddings allows us to generalize to different scenarios. So we could train an embedding model on users, on a set of users, and then we could apply that embedding model to new users and new time periods, as scenario D shows. And we wanted to see if the performance of the model changes when we switch between scenarios. So we devised a controlled evaluation setup, B, C, and D. In B, the time periods are disjoint, but the user sets are the same. I mean, the test data we're using, the test users are seen during training. In C, the time periods of test, the time period of test is the same as the time period of train, but the users are different. And then in D, both the time periods and the user sets are disjoint. And we can see that the performance is on par across the scenarios. Of course, in these results, we evaluated on users from the same distribution, only the user sets are disjoint. Something that could be studied in the future is whether a model trained on a data set, that's out there available, maybe even a small-scale data set, could then be transferred to new data from a different distribution. And this is something which embedding models can do, but traditional classification models that might require a lot of training samples are unlikely to be able to achieve. And there is one other aspect which I'm leaving out for this presentation in order to not talk too much. We looked at what would happen if we invert the time period. So we train on future data and we test on past data, and the impact is not significant. The impact on the accuracy is not significant. And finally, another experiment that we looked at is we looked at what would happen with a different data distribution. Here, Bluetooth close proximity data. So this is the type of data that is being collected by contact tracing apps, containing the parties, so some identifiers for the devices, the timestamp of the interaction, and another quantity, which is a proxy for the distance between the devices. And the data set we looked at was collected from university students over 4 weeks. And we have there are almost 600 people having data in all the 4 weeks. And we computed the probability of identification using one-hop graphs. And we found that more than 26% of them can be correctly identified using our method. I just want to caution that we don't believe that our results apply to contact tracing protocols, such as those by Google and Apple's exposure notification. What we look at is whether data such as the one collected could be identified in a strong attack scenario. And we showed that it could. Finally, now I reached the conclusion. In this work, we proposed a general profiling attack for interaction data, and we validated the approach on 2 real-world datasets, suggesting that profiling attacks can pose a risk to people's privacy. So we believe that they emphasize the need to consider these attacks when assessing whether a dataset is anonymous, for instance, when it would be released. And we hope that this work will inform practitioners. And finally, there's this notion of re-pseudonymization that is being discussed even for contact tracing protocols. It's the idea that you don't just pseudonymize a data set or someone's data when collecting their data, but you change the pseudonyms over time. What we showed is that data that's being re-pseudonymized weekly, on a weekly basis, might not protect against our attack. And yes, this is all. So if you have any questions, I would be happy to answer them.
Yeah, thank you so much. Anna Maria, it was a great presentation. Should I stop the recording now?